beh. Okay, ho registrato. All right. Okay, so yesterday we started touching the weak interaction. Okay, of course we'll continue today in the next following lessons. Before going on with the weak interaction, let me first of all introduce you a new set of quantum numbers which are relevant for any process and which we already implicitly used in our previous exercise. That is the lepton-Clevor number. So, as you know, today we know that there are three generations or three families of leptons, and three of antileptons, to correspond here. So, of those three are charged: electron, muon, tau lepton, and then we have the three corresponding neutrinos. Okay, electron, muon, and tau. And here you see the main features. So you have the electric charge, which is 0 for neutrinos and negative for the charged ones, and the mass, which is pretty light for the electron, as you know, half an MeV. Then it is something like 200 times heavier for the muon, and much, much heavier for the case of the tau. Okay? The tau is essentially, the mass of the tau is almost twice the mass of the proton. Now, so in analogy with the baryonic number that we already introduced quite some lessons ago, each lepton L, or lepton type L, is assigned a conserved quantum number that is called the lepton-Flavor number, LL. So for the electron, it is +1 for electron and neutrino, and -1 for the antiparticles, so the positron and the anti-electron neutrino, and 0 for all the other particles. Similarly, for the muon, it is +1 for the muon and the neutrino, negative for the antiparticles, and 0 for all the others, and the same for the tau. Okay. Now, the important thing is that the lepton-Flavor number is conserved in all interactions and in all processes, just like the baryonic number, with the only exception that we will study in the next week of the neutrino oscillation. Neutrino oscillation is a phenomenon in which neutrino of a certain flavor can oscillate in the quantity of a different flavor. And so in this case, the lepton-Flavor number will be not conserved in the process. But this is the only exception in the standard model. Actually, neutrino oscillation is not encoded in the original version of the standard model. It had to be introduced a posteriori once it was discovered as a new phenomenon. So we studied this in detail. So the lepton-Flavor number of a system of particles, okay, so the initial and final state particle of a reaction, for instance, is given by the number of leptons of a given family minus the number of the corresponding antilepton. So this number here must be constant in any process. Let me give you some examples. Let's consider, first of all, the beta decay that we studied yesterday. So the beta decay is a process where a neutron spontaneously decays into a proton with the emission of an electron and an anti-electron neutrino. Okay? So now we understand why this should be an anti-neutrino and not the neutrino itself, because otherwise the lepton-Flavor number will not be conserved. So in the initial state, we don't have leptons, so the lepton-Flavor is 0, and so it must be 0 also in the final state. And the only way for this to be possible is that the electron is coupled with an anti-electron neutrino, okay? +1, -1, 0. Other examples, okay? So this is the inverse beta decay. So in the initial state, we have a neutrino interacting with the neutron, so the total lepton-Flavor number is 1, and it must be 1 also in the final state, and in fact it is, because we have 1 electron in the proton. And similar here for the muon case. The process that you see here, which is an electromagnetic process, actually is supposed to violate the lepton-Flavor number, because we have a muon in initial state, so with L mu equal 1 and L equal 0, but we have an electron in the final state with L e equal 1 and L mu equal 0. Okay? So if this process should occur in nature, then we would have a clear manifestation of the violation of this conservation law. People is searching for this violation since decades, and you see here the upper limit, the most recent upper limit, which was measured in 2016 by the MEG collaboration. Okay, and as you see, the branching ratio for this decay compared to the total width, okay, so all the possible decay modes is totally negligible. Okay, this is an upper limit, so 10 to the -13 at the 90% confidence level. So there is no evidence at all for violation of lepton number. Okay. Of course, if a violation would be observed, this would be a clear signal of new physics, something new beyond the standard model. That's why it is interesting also to search for these extremely rare, if possible, processes. And you see here a bunch of reactions which are allowed or forbidden by the conservation of lepton number. You can check yourself, okay, all of them, easily. Now, having said that, let me now go back to the weak interactions and let me show you some very basic features that you most likely already know, okay? And then we will go into detail, of course, in the next lessons. So, first of all, differently from the electromagnetic and the strong interactions, the weak interactions are not responsible for the formation of bound states, okay? The strong interaction makes the proton, the nucleons, hadrons in general. Electromagnetic interaction makes the atoms bound, okay, electron with the nucleus. Weak interaction do not create any bound states. Nevertheless, they play a crucial role in some radiative decays, as we studied yesterday, and also in a reaction that occur in the core of stars, for instance, in the sun. So this is, I think I showed already at the very beginning. So this is the proton-proton chain. So the net of nuclear reaction that occur, the most efficient net of nuclear reaction that occur in the core, in the nucleus of the sun, where essentially 4 protons at the end result in a helium nucleus with emission of electrons, of photons and neutrinos and additional protons. Now, the first step of this chain, okay, is regulated by the weak interaction. It is where 2 protons merge to provide a deuteron with emission of electron of a positron and a neutrino. Okay, so if weak interaction would not exist, then also the sun and the universe would not exist as we know it. Now, weak interactions are significantly less intense than the strong and the electromagnetic interaction, as the name says itself, right? And in practice, they are usually masked by them. By this, I mean that the weak process can only occur only if both electromagnetic and strong processes are forbidden by some conservation law. Okay, and this already we said already some examples in the past and also in some exercises. Okay, if there are conservation law that prevents any decay to be strong or weak, then the only possibility for electromagnetic, the only possibility is that it goes through the weak interaction. A notable example of this is the pion decay, okay, the decay of charged pions, sorry, specifically, okay. So the charged pions are the lightest hadrons. They cannot decay into other hadrons. They can only decay into lighter leptons, okay. And these can only occur through the weak interaction, okay. And this is why the decay time of the muon of the pion is so long, okay, order of 3 microseconds. Now, as we also know, weak decays are characterized by relatively long decay times, as the one of the pions that I just saw before, typically of the order of 10 to the minus 8, 10 to the minus 10 seconds, to be compared with the decay time typical of electromagnetic processes, which is 10 to the minus 16 to 10 to the minus 19, or even faster for the hadron decay, okay, 10 to the minus 33, 20 to the minus 24 seconds for strong decays. What about the cross sections of weak process? The cross section of weak process are also extremely small, okay? Although they increase linearly with energy. So at the scale energy of 1 MeV, they are of the order of 10 to the minus 19 barn, can you imagine? So the probability of a weak interaction at this low energy is extremely, extremely small. Although if you increase your energy by 3 order of magnitudes, then the cross section rises up to 10 to the minus 14 barn, which is still extremely small, okay? Consider it is something like 12 order of magnitude smaller than typical cross-section of regulated by strong processes. In addition, neutrinos are the only particles which are exclusively sensitive to the weak interaction because they possess no electric charge and no bulk charge, while charged leptons can interact both through electromagnetic and weak interactions, and the quarks can interact in any kind of interaction, electromagnetic, strong, and weak. And as we already anticipated in one of our first lessons, weak interaction do not conserve some fundamental quantities that are symmetries for the other interaction. So the parity, charge conjugation, PC, time reversal, etc. This we anticipated already a few weeks ago. Today we will study in detail how this was discovered experimentally and how this is encoded in the formal theory of weak interactions. Now, weak interactions are mediated by, as you know, three massive gate bosons. Two are electrically charged, the W plus and W minus, and one is electrically neutral, the Z boson. So we study these into detail. In particular, weak processes, which are regulated by the exchange of a W boson, are called charged current, because they imply a change in the electric charge of the interacting particles, whereas those which are mediated by the exchange of a Z are called neutral currents, obviously. And they do have, of course, different properties. Finally, due to the high mass of the weak boson, which is the order of 80 GeV for the Ws and 91 GeV for the Z, the weak interactions have an extremely short range. This we can calculate in, let's say, the Yukawa-like way. Okay, so the range of the interaction is essentially inversely proportional to the mass of the extended boson. If you put here such a large mass, you obtain a range which is extremely small. So order of 1 per mil of the dimension of the proton, 10 to the minus 3 Fermi. Still a few words about weak interactions. So about now the neutral current processes. So these are mediated by the Z boson, as you see here an example in the diagram. And when this happens, quarks and leptons remain unchanged. So this is an example of a neutrino-electron scattering mediated by neutral current. The neutrino remains a neutrino, the electron remains an electron. Okay? And also, consequently, the electric charge remains unchanged. On the contrary, in all charged current processes, so those that are mediated by the exchange of W bosons, the identity of the quarks and the identity of the leptons changes in the process. Okay, and simultaneously, the electric charge changes by 1 unit of the electron charge. An example of this is, again, the beta decay, okay, the decay of an electron in the proton, that now you see for the first time in terms of quarks, okay? So in terms of quark, what happened is that the neutron is a UDD object, the proton is a UUD object, okay? And in the beta decay, one d quark from the neutron transforms into an up quark, okay, with the emission of a W, which further decay into electron and antineutrino, okay? So this is the way at the microscopic level, or the quark level, how the beta decay works. We have a transmutation of quarks from one flavor to the other, and so of course, and there is a change of electric charge by 1 unit, from minus 1/3 to plus 2/3. Still some more gossip about weak interactions. So charged current process can be divided into 3 categories: leptonic processes, semi-leptonic, and hadronic. And you see here some examples. So leptonic processes are processes which involve only leptons. And one of the examples we saw already yesterday in one of the exercise, which is the decay of the tau lepton. Okay, so the tau transforms into a tau neutrino with the emission of a W boson, which decays into muon antimuon neutrino. Analogous decay you have for the case of electron, just replace the muon with the electron, or with this other charged current process. Neutrino with the electron goes into muon with the electron. So you see the muon neutrino becomes a muon, and the electron becomes an electron neutrino. They change identity when a charged current is involved. Yeah, the second category is semi-leptonic processes. So these involve both quarks and leptons. Again, the notable example is the beta decay of the neutron, okay, that I was showing you before. So a d quark transforms into u quark, and then in the final state we have leptons together with the proton. Okay, or the decay of the pion. The pion is a du bar meson, which you remember, and this decays into a muon and antimuon neutrino, or for the K. So in this case we have yeah, okay. And this is the case for the chemicals. And the last category is pure hadronic processes, so processes that involve only quarks, no leptons. You see here again some examples. So the first example is the decay of a lambda baryon into a proton plus a pion. And what happens is that the U and the D quark do nothing. They are just spectators in the process. The strange quark of the lambda transforms into a U quark that goes to form the proton with the exchange of a W, which now decays into a quark-antiquark pair, forming the pion. Other example, now the lambda 0 into neutron pi 0. Again, the strange quark transformed into an up quark with the emission of a W minus, which decays into a D U bar pair. And then you get the neutron and the pi 0. Finally, the decay of the K plus into a pi 0 pi plus. Okay. Again, it is now the anti-strange quark that goes into anti-up quark with the emission of a W plus in this case to conserve electric charge, which then decays into UD bar, forming the pion and the charged pion to a pi 0. And of course, since quarks cannot propagate as free particles, as we know, but can only hadronize in a length scale which is of the order of 1 Fermi, so the final state of weak interaction involving quarks have to be described in terms of either mesons or baryons. Okay, like the example that you see here. Okay, let's do now an exercise. This is about semi-leptonic decays. So consider two semi-leptonic decays, the sigma plus that goes into lambda 0, positron, electron, neutrino, and the sigma minus that goes into lambda 0, electron, and anti-electron, anti-neutrino. And you know now the masses of the sigma plus and the sigma minus and of the lambda. So first of all, explain why the sigma minus and the sigma plus, the sigma minus is heavier than the sigma plus baryon. Then draw the Feynman diagram for the two decays. Then using the Sargent rule that we discussed yesterday, calculate the ratio between the two decay rates. And then compare the results of point C with a direct calculation based on the information that you are providing in the text. Okay, so let's move on to the blackboard. Okay. So first of all, for the first question, I turn to you. So why the sigma plus and sigma minus have different masses? Try to go back with your memory in the chart and the chapter of the hadrons. So should one be the antiparticle of the other, they must have the same mass, right? Because of the CPT theorem. This is not the case, so they are not one the antiparticle of the other, right? You remember the quark composition of these objects? Okay, I'll tell you. So the sigma plus is an UUS object, okay? And the sigma minus is a DDS atom, okay? So these explain why the charge is different, okay? And also why the mass is different, because you know that the D quarks are slightly heavier than the up quarks. And together with the sigma 0, which is a UDS, they form an isospin triplet. Okay. You can check yourself in the hadron chapter. So point B is to draw the two decays. So let's do the way we've just learned for semi-electron decays. The sigma plus is a UUS baryon, so it's UUS baryon. And at the end, we must have a lambda 0 plus positron and electron. So the lambda 0 is also a UDS. So what happened is that the strange quark remains strange quark, which is spectator. The U quark remains a U quark, which is also spectator. And then the U quark, the other U quark becomes a D quark. Okay, so a weak process. So with the exchange of the W plus, which then decays into the positron and the neutrino. Okay. Similarly now for the sigma minus. The sigma minus is a DDS. Again, we are also here number 0. So strange remains strange. The D remains D. And now the D becomes U. This time with the emission of a double minus in order to allow for electric charge conservation. And so this must decay into an electron and an electron activity. We also see that in both cases, the electron level number is conserved. Okay, it is 0 in the final state and 0 in the initial state in both cases. Okay, now let's move to the third point. So the third point, so using the Sargent rule, calculate the expected ratio between the decay rates of the two decays. Okay. So for the Sargent rule, if you remember, we need to calculate the E0, so the energy available in the final state, as we did yesterday. So the E0, for the case of this plus, calculate as the mass difference. Okay, so we give delta M sigma plus. That is the mass of the sigma plus barrier minus the sum of the mass in the final state. So this the mass of the lambda 0 plus the mass of the electron plus the mass of the neutrino. The mass of the neutrino we can neglect. It is extremely small, so has nothing to control. So let me just put the numbers. So it is 1,189.37 MeV times 115.68 MeV minus the electron. And the result is 73.18 MeV. We now do the same for the sigma minus. So we have is a bit heavier, as we showed before. So nice, 0.68 times 0.11. The result is 81.26. Let me write it here. Okay. Can I clear? Now, by using the Sargent rule, the ratio of the two decay rate, like this, sigma minus plus or minus. So this goes like the fifth power, okay, of the energy. So let's now put the numbers. And the result is 0.51. It means that there is, sorry, this is a minus. There is a preference. The decay of the sigma is more probable than the decay of sigma plus. Now, the point D asks us to check these results with a direct calculation based on the information given in the text, which are the branching ratios and the decay times. So, again, R is equal to W sigma plus divided by W sigma minus. And as we know, this is the branching ratio divided by the decay time for each of those. So this is gamma I divided by gamma tot for the plus case divided by the tau plus, and gamma I divided by the total gamma for the minus case divided by the decay time for the sigma minus. So this is nothing else than the branching ratio for the sigma plus divided by the branching ratio for the sigma minus times the decay time of the sigma minus divided by the decay time of the sigma plus. So all this information is provided in the text of the problem, so we can substitute. And so we have 2.0 10 to the minus 5 divided by 5.73 10 to the minus 5 times 14479 10 to the minus 10 seconds divided by 0.8018 10 to the minus 10 seconds. And the result is 0.64. So the question is there a discrepancy between the two, or the two are consistent with each other? How would you reply to this question? Look at the text of the problem shared. So the numbers that are provided in the text, which are those numbers here, of course, are not exact numbers. These are measured quantities which come with an error, an experimental error. So the question is, are those two consistent with this experimental error? And this we have to check. So we have to propagate the error to this formula here. Okay. The uncertainty are provided on the text as well. That is just write them here. So the uncertainty for the branching ratio plus is 0.5 10 to the minus 5. The uncertainty on the branching ratio minus is 0.27 10 to the minus 5. The uncertainty on the decay time plus is 0.0026 10 to the minus 10 seconds. And uncertainty on the tau minus is 0.011 10 to the minus 10 seconds. Okay. So we have to propagate these uncertainties into the master formula. And so one can, for instance, use the standard propagation error formula, okay, for indirect measurements. So you know already pretty well. So this is dr in the branching plus squared times the sigma tension plus squared plus GR V tension pressure minus squared sigma ventilation squared here plus we are getting the tau plus squared sigma tau plus squared plus we are with tau minus squared sigma tau squared, right? So this you can do yourself for exercise. You can take all the partial derivatives of the main formula and substitute all the values. At the end, this is 0.16. So this is the plus or minus 0.16. So the two are in agreement. Okay. Okay. Now, let's go back to the slide. And let's now study how parity violation was discovered in weak interactions. Okay, this is a crucial point, okay, of weak interactions. So in the early 50s, it was observed that the K-plus meson can decay both into pi 0, pi plus, but also into pi plus, pi plus, pi minus. Okay, what is the problem here? Now, let's calculate the parity of the first one. That is minus 1 to the L, and then we have the intrinsic parity of the pi, which is minus 1 squared. These are low-lying states, so L is equal to 0. Overall, the parity is positive. What about the other? If you now calculate the other, we have now 3 pions, so we have an additional minus sign, and the parity is negative. So we have found that the same object, the K plus, can decay into two final states, which are eigenstates of different parities. And so this suggested the revolutionary idea at the time that weak interaction must violate parity conservation. Now, this was not a good news for many people, because parity is a symmetry of space-time, okay, like rotations. And so there was a lot of skepticism, okay, in the physics community to accept that parity should be violated. But it was also realized that in practice, no experimental proof of parity conservation existed at the time. In addition to that, those two brilliant guys, Lee and Young, scrutinized all the experimental results based on weak processes that were available at that time, and indeed found that none of them had studied the dependence of the interaction on a pseudo-scalar term, where pseudo-scalar term is an object that changes sign under parity, as we studied already, okay? Such as the helicity, so sigma of Q times P, spin and momentum. Those two guys got the Nobel Prize in 1957 for this idea. And they also, here. Yeah. So here you see many different physical observables: position, momentum, angular momentum, electric field, blah, blah, blah. Okay, and so some of them are vectors, some other axial vectors, some other pseudoscalar, interscalar. And then you see what happened when you apply the parity operator. Okay, so some remain the same, others change sign. In particular, this longitudinal polarization is one of those that change sign upon application of the parity operation. Okay, it is a pseudoscalar. So Lee and Young realized that if the Hamiltonian of weak interaction would include a pseudoscalar term, such as this one, then parity must necessarily be violated in weak interactions. And they also proposed several experiments. They were theoreticians, so they proposed several experiments to test the presence of pseudoscalar term in weak processes. Okay. Now, this idea was taken by Madame Hu, that you see here in the picture, who made in 1957 a brilliant experiment, very smart experiment. So to study the possible dependence on a pseudoscalar term on weak interactions. So the idea of Wu was to study the beta decay of polarized cobalt-60 nuclei, okay? And the decay is written here. So we have cobalt nuclei that decay into excited nickel nuclei plus electron and neutrino. And let me also remark that the energy value in this decay is rather small, okay? It's only 0.3 MeV. Now, the spin of the cobalt nuclei, which is 5 in the unit of h bar, was aligned in a strong magnetic field. Okay, so you see here the direction of magnetic field, and this is the direction of the spin of our cobalt nuclei. Now, the cobalt decays beta into the nickel, okay, and the nickel has a spin 4. First of all, okay, it is created in excited state, and then it decays in the ground state to the emission of 2 photons. But in this electromagnetic decay, it maintains the original polarization. Okay, so the nickel is now here. It is 4, okay, but it is still aligned with the magnetic field and with the original moment, the spin of the cobalt. Okay, and then the other two objects that are produced in the decay, which are the electron and the neutrino, in order to allow for angular momentum conservation, they have also to be aligned with the magnetic field. Okay, so we have plus 4 plus 1/2 plus 1/2 give us 5. Okay, so this is the only possible configuration that allows angular momentum conservation in the decay. Okay, we can see this here. Okay, so all the objects here, so the cobalt, the nickel nuclei, and the electron and neutrino have all the spin in the same direction, which is the direction of the magnetic field. Now, let's now describe the experiment that she did. So, so this is our cobalt crystal. Okay, and then we have here a scintillator, which is a detector that was used to detect the emitted electrons. Of course, there is no way to detect the emitted neutrinos. So a scintillator counter located on one side of the CO sources was used to detect electrons emitted in the same direction of the magnetic field or in the opposite direction after inverting the magnetic field. Okay. So this is the situation before the decay. Now, after the decay, the cobalt transformed into nickel plus electron and neutrino. Okay. So one possible configuration is the one where the electron is emitted opposite to the magnetic field. So the magnetic field is still in this way, but the electron is now opposite. So the momentum of the electron is this way. Of course, but the spin must stay the same, okay, in order to allow angular momentum conservation. So the spin can always point to the magnetic field, but the momentum can be opposite in principle. Okay. And so this configuration, one can measure the intensity of the electron in the scintillator. In this configuration, we can call this I minus or IT equal pi. The other possibility is that the electrons are emitted in the same direction of the magnetic field, okay, so from left to right. Okay. In this configuration, we call I plus or IT equals 0. Okay. Of course, the scintillator was always positioned in the same place, but the only difference is that the magnetic field was inverted. Okay. So we have these two possibilities, and let me note you that these two possibilities are one the parity mirror of the other. So suppose here we have a parity mirror, which is a mirror that, as you know, invert coordinates, invert momentum, but does not touch angular momentum or spin. Okay. So in fact, if you compare left with right, the momenta are inverted, but the spin remains the same. This is a parity mirror spin. Okay. Now, if the process were parity conserving, so no parity violation, then the intensity of the electrons detected parallel or anti-parallel to the magnetic field, or to the orientation of their spin, must be the same, okay, in case of no parity violation. So the E theta equals 0 should be equal to E theta equal pi, okay, or more general, E theta must be equal to E of pi minus theta, okay, back to back. Where the angular distribution of the intensity, so this I theta, can be parameterized in this way: 1 plus alpha, then we have this pseudo-scalar term, okay, sigma plus E divided by energy, and this can be also written in this equivalent notation with alpha d over c cos theta. Cos theta is the angle between these two vectors, where alpha is a parameter that ranges from -1 to 1. So this is the theory, okay? So first, under parity transformation, the term, the pseudoscalar term here, if present, must change sign because it is a pseudoscalar term. Okay, and so if one observes this, one is observing a parity violation. So in order to have a parity conservation, the alpha parameter must be 0. This means that this term is not present. Okay. Now, experimentally, what measures? So experimentally, they measure of course, the angular dependence of the intensity of the electrons, okay, which is parameterized as the polarization times this, let's say, net helicity of the electron, which is the asymmetry between the intensity of the electron parallel to the magnetic field and anti-parallel to the magnetic field. Okay, E plus minus E minus divided by E plus plus E minus. So E plus is the measured intensity of the electron with momentum parallel to the electron spin, E minus anti-parallel. So let's now look at the result of the experiment. First of all, let me tell you that initially, at the beginning, the crystal of cobalt was cooled down to 0.01 Kelvin, so very, very close to the absolute zero. And in this configuration, it was possible to obtain a polarization of 60%. So 60% of the cobalt were polarized in the direction of the magnetic field. Then, of course, as time passes, the crystal started to warm up, and so the polarization started to be lost. Okay. So you see here the measurement. In the vertical axis, you see the counting frequency divided by the counting frequency at 0 polarization. And when the polarization was very high, so when the crystal was still very cool, they obtained something like 0.8. Okay. Then the crystal started to warm up, the polarization started to be lost, and at the end, after 8 minutes, there was no polarization anymore. Okay. So the measure important is in this one here. And this was done with for the case t equals 0. So for the case where the electron momentum was parallel to the magnetic field. Then they switch the magnetic field in the other direction, and they measure again the same ratio. Okay, and they found a completely different result. Okay, again you have to consider this region here, where the polarization was sufficiently high to make the measurement. Okay, so you see 0.8 with 1.2. So there is a clear left-right asymmetry in the direction of the emitted electrons. Is that clear? So the experiment found that the intensity of the electron measured in the scintillator was different after inverting the magnetic field. So I plus was different than I minus, and so this asymmetry was non-zero, indicating a clear left-right asymmetry in the direction of emitted electrons. In particular, the experiment showed that electrons are preferably emitted in the direction opposite to the magnetic field. This is the case, okay, where the two are back-to-back, so opposite, and you see here that the ratio is much higher than in this case, okay? So there was a preference in the decay for the electron to be emitted opposite with respect to the magnetic field direction. And so, in other words, they are emitted preferably with negative helicity, because the spin always points to the magnetic field direction, okay? So why I'm saying here preferably? Because those electrons were not relativistic. Let me remind you that the energy available in the final state was only 0.3 MeV, okay? Being not relativistic, you can always find a reference frame which is faster than the electron, where the electron has a positive helicity, okay? That's why it was only the majority of them, but not all of them, okay? And this depends on the ratio between B and C, so how much the electrons were relativistic. So the two configurations, which are the parity mirror one of each other, one is the favored and the other is the disfavored, according to the experiment. Okay, and this unambiguously demonstrates that parity is violated in weak interactions. Okay. In particular, the experimental data were consistent with alpha being -1, so to the very lower limit of alpha. Alpha, in principle, is ranging from -1 to +1, if you remember. Okay, but experimental data were consistent with alpha being indeed -1. So this means that not only parity is violated in weak interaction, but it is maximally violated. And this will be more clear now in a moment. Now, the following year, is 1958, the famous Goldhaber experiment revealed that the helicity of neutrinos is always negative. This means that the spin is always opposite to their momentum. Furthermore, since neutrinos are essentially massless, okay, they also have always left polarity. So all the neutrinos are left. And then it was also shown similarly that the antineutrinos are always right-handed. Okay. Now, in fact, right-handed neutrinos or left-handed antineutrinos have never been observed in nature. And this is indeed a clear manifestation that parity is maximally violated in weak interactions. Okay. What about charge conjugation? Well, if parity is violated in weak interaction, then also charge conjugation must be violated in weak interaction. And the reason is the following. As I was just mentioning, no left antineutrino exists in nature, and no right neutrino exists in nature. In nature, you can only have left neutrinos or right antineutrinos. Now, when you apply the charge conjugation operator to a left neutrino, you get a left antineutrino, which does not exist. Similar, when you apply the charge conjugation to a right antineutrino, you get a right neutrino, which does not exist. So charge conjugation is, as a consequence, also violated in weak interactions. Okay. What about the combination of C and P, CP? Well, if you apply both operators, then we obtain something which is observed. So CP of a left neutrino turns out to be a right antineutrino, which is indeed observed. You are switching now particle to antiparticle on the left to right, and this works. Also, CP for the antineutrino right gives you a left neutrino, which also is observed. Okay. So if you move now here into the diagonal, you find something that indeed works. It is observed in nature. So one would claim that P is violated, C is violated, CP is conserved. These turn out to be also wrong, as we will study next week. Also, CP is actually violated in weak interaction. It is a very small effect of the order of per mil, as we will study, but it has very profound cosmological consequences. Okay, let's make a break here. Okay, let's combine at 12:10. So we recombine at 10 past 12.
Sì, sì, comunque sì.
Ok, da casa vedete la slide?
Sì, sì, vediamo.
Ok, allora riprendiamo adesso. Okay, so we discussed how experimentally it was found that parity is violated in weak interactions. Okay, so it was a big surprise for the physics community, but it's life, that's nature, actually. Okay, so now we have to encode this observation into the theory of weak interaction, and this is a major step. So, at fundamental level, QAD and QCD share the two following important features. So first of all, they are both mediated by massless neutral gauge bosons, either the photon and the gluons. And as we know, they conserve parity and also charge conjugation and also time reversal and also CP. Okay? The difference between QAD and QCD, the main difference is that the gauge bosons, the gluons, carry color charge. And this makes the theory non-abelian and self-interacting, if you remember. Now, charged current weak interaction differs in almost all respects with the other two. First of all, they are mediated by massive charged bosons, the Ws, so they are massive and also charged, which couple together fermions which differ by 1 unit of electron charge, as we saw, and they violate parity and also C, T, and CP. Okay, so everything is different here. Now, and as we've shown already in the QAD chapter, the parity conservation in QAD and also in QCD is a direct consequence of the vector structure of the vertex interaction. So if you remember, we showed that parity is conserved in QAD because the vertex interaction is a 4-vector current. Okay. So parity violation in charged current weak interactions suggests that the form of the vertex interaction must be different, cannot just be a vector current, otherwise parity will be conserved. However, we have not infinite possibilities because we are constrained by the Lorentz invariance. Okay, so requiring Lorentz invariance, the only types of current that are possible are those shown here. Okay, so these are given in the form of bilinears, psi bar, 4x4 psi, where 4x4 is a combination of the gamma matrices. So the complete list of possible currents, so that fulfill the Lorentz invariance, is the following: scalar current, pseudo-scalar current with gamma 5, vector current, which are the ones that we know from QAD and QCD, axial vector current, gamma mu gamma 5, and then tensor current. And the number of degrees of freedom that you see here in the last column reflect the number of polarization states exchanged by the boson. You know, it is 4 for the case of the virtual photon, 1 for scalar boson, 6 for tensor boson, etc. Now, since the Ws are vector bosons, so spin 1, okay, then of course we are searching for a vector current. Cannot be scalar, cannot be tensor. Okay, and so we have two possibilities actually: vector current and axial vector current. And so in the most general case, we can consider the combination of the two. So let me introduce now two different coupling constants, GV and GA, which are the coupling constant of the vector and of the axial vector currents. And so let's consider just a linear combination of these two possibilities. And then we will see what values are possible for GV and GA for the coupling constants. So our general current for charged current interaction, weak charged current interaction, is GV, JV plus GA, JA. So GV is the standard vector current multiplied by the vector coupling, and GA is this axial vector current, this guy here, with the gamma mu gamma 5 matrices multiplied by the GA coupling constant. And so this we can write also in a more smart way, in this way. So we put the spinor outside, and then inside we have the decoupling constant with the proper Lorentz matrix combinations. Okay. Let's see what happened under parity operation. So let me call U prime the, sorry, I have to stop here. Okay. So let me call U prime the parity transformed spinor. So this is P U. And if you remember, this is just gamma 0 U as we write. Okay? So the parity operator on a spinor is just gamma 0. Okay? This will show already. And for the adjoint spinor, so U bar prime is similarly U bar gamma 0. Okay. Now, and in general, the current, okay, we cannot is a 4-vector in general, so we can write as G0 and then minus JK with K equal to 1, 2, 23. Time component and spatial components. Okay. So let's apply the parity operator to the 0 component of a vector current. So 0 vector. So this we can also call J0 vector prime. It is the parity transform. So this is U bar gamma 0, U bar prime gamma 0, U prime. Okay, the transformed current is given in terms of the transformed spinors. Okay, so now we can substitute this here. So this is U bar gamma 0, then we have gamma 0, and then we have gamma 0. Okay, now remember by the properties of the Lorentz matrix that this is Dirac matrix, this is just one. And so we have U bar gamma 0 U, which is the untransformed zero component. Okay? So the parity operation doesn't do anything on the zero component of the vector current. Okay? We obtain the same as the untransformed. Let's work out now the time component, JK vector. So this is a JB K prime. Okay? So this is now U prime, gamma K, U prime, and this is U bar 0, gamma K, gamma 0, U. Now we apply the properties of the Dirac matrices. So when we walk to, we have to choose sign, if you remember. So this is minus U bar, gamma 0, gamma 0, gamma K, U. Again, this is 1. So we got minus U bar gamma K U. So this is now minus the spatial component of the vector current. Okay. So under parity, we get a minus sign here, the spatial component. Let's now do the same exercise on the axial vector current. Okay. So E J0 axial vector. It is J0 prime. So this is U bar prime, gamma 0, gamma 5, U prime. So this is U bar, gamma 0, gamma 0, gamma 5, gamma 0, U. Let's first swap those two here. So we get a minus sign, U bar, gamma 0, gamma 0, gamma 0, gamma 5, U. So this is again 1. And so we have minus U bar, gamma 0, gamma 5, U. It is minus JB prime. So in the case of axial vector, it is now the time component that can sign on the parity operation. Let's work out on these spatial components. Yes, the vector J, K, A prime. So we have now gamma k gamma 5. Fine. Fine. So this is u bar gamma 0, then we have gamma k, then we have gamma 5, then we have gamma 0. Am I missing something? 0 k 5 0. Yes, correct. So let's swap those two here. We get minus u bar gamma 0, gamma k, gamma 0, gamma 5 u. Let's now swap those two here. So we get another minus sign. So we get a plus sign now. U bar, gamma 0, gamma 0, gamma k, gamma 5 u. This is 1. So U bar, gamma k, gamma 0 u, which is plus j k k. Okay. In this case, the time component changes sign, the special component does not. Okay. Keep all these results with you. Now we'll see everything. Posso cancellare da casa?
Just 2 seconds, please.
Okay. Sorry?
Just 2 seconds, please.
Ah, yes, okay, sure. Tell me when you're done.
All right. So thank you, it's done. Sorry, my camera just went a bit weird for a while.
Okay, no problem. Okay. So let's now apply the parity operator on the scalar product of two vector currents. So this is J V scalar B. So this is J V prime or J V prime. It is J V 0 scalar J V 0 minus J V K J V K. All this is prime. Sorry. That's under parity operator. 0 prime, 0 prime, 0 prime, 0 prime. Okay. Now, we applied the result that we derived before. I will skip the integral passages. So you will immediately see that putting the proper sign, this is just JD scalar JD. So this is unchanged. This you change sign, but you multiply to minus sign. At the end, you get plus. So nothing changes. Okay. So the scalar product of two vector current is unchanged by parity relation, by parity operation. Let's now do the same for the scalar product of two axial vector currents. This is J prime A, scalar J prime A. This is J0 prime A, scalar J0 prime A minus J K prime A, J K prime A. Again, you substitute the results we had before, and you find out that also in this case, it is just the same. The two minus sign compensate. What about now the mixed scalar product? JV scalar JA. So this is J prime V scalar J prime A. It is J0 prime V, J0 prime A minus J K prime B, J K prime A. Again, you substitute, and now you get something like this. J0B, J0A minus JKB, JKA. So this is indeed minus JB scalar JK. And this is our crucial point. So the parity operator does not change the scalar product of vector current nor of axial vector current, but it does when you mix the two. Let's see what is now the consequence of this. Okay, so this is the result that you have in the blackboard. So the mixed scalar product change sign under parity. Now, why is this relevant? Because as we know, the matrix element MFI is proportional to the scalar product of two currents. Okay, this we studied already in QED, in QCD. And so the combination of a vector and an axial vector current can provide a mechanism to explain the observed parity violation in weak interactions. Okay. So let's see how this works. So let's consider the inverse beta decay. So neutrino into the d quark and goes electron and up quark. Okay, with the current in the general form where we take the combination of the two. Okay, so we are still general at this level. So it's U bar P3, which is the final state. Then we have our interaction and the UP1, and then the same for the lower vertex. Okay. Now, when you calculate your matrix element, at the end, you have to calculate the scalar product of the two currents at the upper and lower vertex. And when you do so, you get pure vector current, which is this one times this one, pure axial vector current, this one times this one, but also two mixed terms. Aha. You understand the point now? If you now apply the parity operator on your matrix element, then the mixed term will change sign. And so we found the mechanism to introduce parity violation in weak interactions. Let's be now more precise into this. So let's compare now those two objects. Essentially, the parity violating term is this mixed term, where we are mixing now the vector and the axial vector currents. Okay, and the relative strength of the parity violating part, okay, of the matrix element compared to the parity conserved part is given by the ratio, this ratio of the corresponding coupling constants. Okay, so this ratio would be 0 if GV is 0 or JA is 0. And we know that for QED and QCD, JA is 0 because the current is purely a vector current. Okay, and that's why we don't have parity violation in QED and QCD. Okay. On the other hand, it is maximal if GV is equal of GA in magnitude. If they are the same side, then we have a maximal parity violation. And we can have a maximal parity violation in two different prescriptions, in two different ways. Either as the sum of the two, B plus A, in this case, JI is equal to GV, or the difference, V minus A. In this case, GA is equal to minus GV. In both cases, we have a maximal parity violation. But the consequences of V plus A or V minus A are completely different. V plus A, one can show, or will not show this, but one can show that if the weak charged current were V plus A, then they could couple only with right-handed fermions and left-handed antifermions, which is in total contradiction with experimental observation. However, if one considers the V minus A combination, okay, so GA equal minus GV, then charged current coupled exclusively to left-handed fermion and right-handed antifermion, which is in perfect agreement with the observation. Okay, so we found now our way to combine the vector and the axial vector to make charged current properly and accounting for parity violation. Let's do this. Okay. Okay. So vector minus axial vector means that GV GA is equal to minus GV. Okay. So we can write this as GV equal to G and GA equal to minus G. Okay, so we can just introduce one single coupling, G, which is common, but taking care of the proper sign. Okay. So the current G move, as we've seen, we're starting with the general case, which is a combination of the two. So in general, this is GV JV plus GA JA. It is U bar T prime GV then mu plus GA gamma mu gamma 5 U B. Okay, so this is our general assumption. Just take a linear combination of the two. Now we apply our V minus A condition. So this is G U bar T prime gamma mu minus gamma mu gamma 5 U. Or if you like, G prime, fine. Then we have gamma mu 1 minus gamma 5 G. Where G is the global charged current coupling. So you can also write G is equal to G W if you like. Okay. So our bilinear term is this value. So this is our 4x4 combination of Dirac matrices. Gamma mu 1 minus gamma 5. And the vertex factor, the one that enters into the current applying the Feynman rules of the charged current interaction, is with all the proper coefficients minus I G 1 divided by 2 square root of 2 gamma mu 1 minus gamma 5. Okay. So this is the ingredient that you have to put in your current as a vertex factor when you apply the Feynman rules for charged current with interaction. Just to remind you that for JD, the vertex factor was minus I JD gamma nu. And if you take JI as the vector charge, it is I gamma nu. This is what we do for the model scattering. So we can write now our current in the proper way. So the demo charge current, okay, this is V bar prime. Then we have our vertex factor, which is big right here, minus I G 1 2 gamma nu 1 minus 5, and then we have the initial state spinor. The factor 1 of 2 square root of 2 is only for historical reasons. Okay, it was there at the beginning, then it was there. It's just a factor, it's not no impact. And so this we can at the end write as J mu CC as minus 5 G U bar prime. Then we have 1 half gamma mu 1 minus gamma 5 U. And this is our charged current. Okay. So this is the way parity violation is encoded into the V minus A with theory with interactions. Okay. So back to the slide. Let's summarize these results in the slide. So, okay, so this is the full expression of the weak charge of current, okay? Let me also note that if you look inside here, you would recognize the left-handed projection operator, EL 1/2 1 gamma phi that we introduced back a couple of months ago. Now, for comparison with QED and QCD, so this is the current, the charge current, and then this is what we know already from QED, okay, like for the vertex current for QED, and for QCD, which is exactly the same. So in both cases, we have a vector current, but in this case, you have to take into account the point factor. Okay, so now we have all three together here. You can compare. Now, as we've seen already, a vector current can always be decomposed into a left-handed and a right-handed fermions. Okay, so we've done this expansion already in the past, and we also seen that in QED only the pure left and the pure right terms survive. We've shown that the mixed terms are zero; they do not contribute to the current, and so to the cross section. Now, this was for QED and also QCD. But in charged current with interaction, as I will show in a moment, also the right term goes to zero. So let's show this. And so, in other words, only the left term survive in charged current with interaction. So let's see why. So let's first of all show that the right current goes to zero in charged current with interactions. So this is proportional to U bar right, 1 move, 1/2, 1 instead of 5. Okay, right, so we are taking only right-handed spinors and adjoint spin. Now, the right-handed spinor can be obtained by applying the projection operator, okay, the carrier projection operator. So this is U PL, 1/2, 1 minus 5, and then PRU. So PR is the right-handed projection operator. When applied to the spinor, give you the right-handed spinor. PL is the left-handed. When applied to the adjoint spinor, give you the right-handed adjoint spinor. Is the contrary for adjoint. Okay. So now we can make explicit those two projectors. So this is U bar, and then we have 1/2, 1 minus gamma 5. This is the left-handed projector. Then we have 1/2, gamma mu, 1 minus gamma 5, and then also here with 1/2. And now we have the right-handed, so with the plus sign, 1 plus gamma 5. Let's collect the things. So this is 1/8. So we're taking all these factors outside. U bar 1 minus 5. Then we have gamma mu minus gamma mu gamma 5 times 1 plus 5. Okay. So this is 1/8, but 1 minus 5. And now we take the products here. Okay. So we have gamma mu plus gamma mu 5 minus gamma mu gamma 5 minus gamma mu gamma 5 gamma 5. This goes away. This is 1, and so it also goes away. And everything is 0. So there is no right current in charged current with interaction. A smarter way to show this, and much shorter, is just to make use of the projector. So is JRR, you can write that is UR, gamma mu, 1/2, 1 9.5. This is UR. Okay, so we start from the same point here, but now we apply, recognize that this is just the direct projector. Okay, UR, then we get gamma mu, and this is now just the left parallel projector acting on the right parallel as a spinner. Okay, the two are orthogonal, so this is 0. Okay. So this was the first part of the demonstration. Okay, so we show that also the R current is 0 in interaction. Now we have to show that the current that we derived before only deals with the left fermions. Okay. Let's take this for particles. We will do next for the antiparticles. So this is that we derive the minus Ig, then we have G squared 2, then we have 1/2, not that it is the control schema. U bar P prime, 1/2, mu 1 minus 5, and then U P. So this is the one we derived before. This can be written as minus 5, G over root of U, this is the string. Then we have 1/2. And now we can write this guy here is equivalent to 1/2, 1 plus 5, gamma mu, 1 minus 5. And then we have this. This we will see. I will show you later why. Okay, for the moment, just take it as true. Okay, now it's trivial algebra. So this is minus 5, G over root of 2. Then we have U bar P prime, 1/2, 1 plus gamma 5. Gamma mu, and then we have 1/2, 1 minus gamma 5, U P. Now, this is the right projector, right chiral projection, and this is the left. So this is going to be minus 5, G over 2. When you apply the right projector onto the adjoint spinner, you get the left adjoint spinner. Okay, then you have to move. And when you apply the left of the spinner, you get the left. So this is just a J left. Okay. So the only contribution that survives in our current is indeed the left component. Now I have to demonstrate this right here. Let's do on the contrary. We start from the final result and the initial. So 1 plus 5, gamma mu 1 minus gamma 5. Okay, so this is 1/2, gamma mu plus gamma 5 gamma mu 1 minus gamma 5. Now we swap those two here, so it is 1/2 gamma mu minus gamma mu gamma 5 1 minus gamma 5. Put gamma mu outside 1 minus gamma 5 1 minus gamma 5. It is sorry. So this is half gamma mu 1 minus 2 gamma 5 plus gamma 5 squared. This is 1 and 1/2 gamma mu 2 minus 2 gamma 5. And so we did again gamma mu 1 minus. Okay. What about antiparticles? Antiparticles, so now using antiparticle spinor, the B, the situation is opposite. So when you apply the left projector on the antiparticle spinor, this is 1/2 1 minus gamma 5 B. This turns out to be a right-handed antiparticle spinor. When you apply the right projector on the spinor, this is 1/2 1 plus gamma 5 B. This is now the left, just the contrary. And for adjoint antiparticle spinors, P R B. Now we have the contrary of the contrary, so we get back to the standard scenario. 1/2 1 plus gamma 5 is the right adjoint antiparticle spinor. And similarly, P left B is not 1 minus gamma 5. Adjoint antiparticle spinor. Okay, so let me derive the current for the case of antiparticle. So the structure, of course, is the same. So we have minus I G divided by square root of 2 V bar P prime 1/2 gamma mu 1 minus gamma 5 V P. So this is minus 5 G on square root of 2 V P prime. Then we apply the strict that I showed before. So this is half 1 plus 5 over 1 minus 5. And then we have P. So this is minus 5 G equals 2 V adjoint P prime 1/2 1 plus and 5. Then we have mu. Then we have 1/2 1 minus gamma 5. Okay, so now this is divide this spinor. We have to deal with antiparticle spin, so this is minus I divided by the square root of 2 V right V prime and mu V right. So this is for the antiparticle right. So let's summarize this in the slide. So as we just learned, only left-handed fermions and right-handed antifermions can participate to the charge current weak interaction. Okay? There are no other possibilities. And this is also the sense of the maximally violation of the parity. Okay, so suppose we have this process here where we have a right-handed antiparticle, antifermion, with interacting with the left-handed fermion. So this is allowed. You apply parity, you get a process where now we have a right-handed particle interacting with the left-handed antiparticle, and it is forbidden. Okay. So in this sense, parity is maximally violated in weak interactions. Let me say a few words about the propagator now. So differently from the photon, of course, the charge current weak boson, the Ws are massive, actually very massive, order of 80 GeV. And so when you calculate, when you consider the propagator, you have to include also a mass term in the denominator. Now let's consider a low energy case, a low energy process. This means that Q squared is much smaller than the mass of the W squared. Okay. If this is the case, so for low energy charge current weak processes, then one can neglect the Q square in the propagator, and the propagator is just G mu nu divided by the square mass of the W. So there is no any more dependence on the Q square in this limit. Okay? Let's derive first an example, and then we comment on this. So as an example, we derive the matrix element of the muon decay. So for the muon decay, we've seen yesterday, the minus goes into the minus plus the minus. Okay. Antineutrino and neutrino must be accounted for, allowing lepton number conservation, of course. Okay. So the decay we have seen also yesterday. So we have our muon that goes into a muon neutrino with the exchange of the W minus, which decays into an electron and an anti-electron neutrino. So we have two vertices, mu, no. We can put also the four momenta, P1, P3, P4. So yes, okay. So and this is the sorry, this is the new vertex. So we can proceed in the way we know, okay, using the Feynman rules. So we start minus phi and f phi. So we first consider the upper vertex. This is u bar P3. Then we have the vertex factor minus phi g divided by 1/2 gamma 1 minus gamma 5 so u p1. This is the current of the upper vertex. Now we have the propagator of the W boson, which is massive. So this is minus phi G mu divided by Q squared minus M W squared. And then we have the current of the lower vertex. At the lower vertex, we have similarly u bar 2, then we have the vertex factor minus phi d by the square root of 2 1/2 gamma mu 1 minus gamma 5. Now we can multiplied by minus I, so we can obtain the 2mxi, okay? So what we have here, we just put the constant outside, minus g squared to the 8, and then we have u bar 3, and we move 1 minus 1, 5, u 1. Then we have the propagator, g mu divided by 2 squared minus m squared w. And then we have u bar 3 gamma nu 1 minus gamma 5. In this case, oh, sorry. In the final step, we have an anti-neutrino, so we have to use the V spin-off. Okay, so we use the V. Sorry, V. P4. No, sorry, this was the upper byte. Sorry, no. This is here. No, okay, this was the other this. Okay, so this was strong. So this was P4. Okay, so this is the anti-neutrino, so you have to use the antiparticle spin-off here. Okay, and also here. Let me check if all is fine. Okay, now we know how to write this in terms of left spinors. So this is and I equal to minus g squared by a. Then we have u left 2, then move u left 1, g mu q squared minus n squared w, and then u have 4 gamma nu v r. Okay, so the antiparticle is right, the antifermion is right, all the terms are left. Okay. Now, the muon decay is a low energy process, okay? So we are indeed in the region where we can neglect Q squared with respect to the mass of the W squared. Okay, so we can neglect this term here. We get a minus sign which cancels with this minus sign here. And so for this process, we have at the end the G squared divided by 8 and W squared times all the rest. Bar L 2 31, which is just V mu. And then we have Q bar L P2, P. Sorry, this P3 a bit tired. Okay. And then gamma nu, and then V bar. Two more minutes and we are done. Okay. So this was an example of just the muon decay. Okay. In general, we can write down the matrix element for any low energy charged current weak process in this way. Okay, where we have this factor here, this squared divided by 8 square mass of the W, and then we have our currents, which are V minus A currents. Now, all this quantity is independent of Q square because we lost the Q square dependence in the low energy approximation where it disappeared from the propagator, right? Okay. But physically, the Q square independence of the interaction corresponds to replacing the boson propagator with the Dirac delta function. There is no dependence on Q square, so it's just a point-like interaction, okay? Like the one you see there, which was indeed the original Fermi idea, if you remember from yesterday, okay? the Fermi idea of a point of a 4 Fermi point-like interaction. So according to the Fermi approach, the matrix element for these 4 Fermi point-like interaction must be given here in this way. So we have currents, and then we have the Fermi constant. Of course, this object here does not fulfill parity violation. It has not a B minus A structure. So we have to correct these for the B minus A structure. So according to Fermi, this low energy process, so Q square independent process, would look like this. The matrix element would look like this. Okay. So now we have the proper B minus A currents, and we have our Fermi constant on top of this. And now you can compare the two. Okay. The two are both right in this approximation. And so you can make this comparison to evaluate the relation between the Fermi constant and the G, charge current coupling. So this is done here. Okay, so if you equate the two, you get this relation. So you can derive now G squared as a function of the Fermi constant. Okay, and we have here the mass of the W in between. Now, if you remember from QED, the alpha electromagnetic is the square of the electric charge divided by 4 pi. Okay, so this is the way the electric charge is related to the electromagnetic coupling. We can do the same here. Now our charge is G, small g. Okay, so we can construct our charged current weak interaction coupling alpha W as G squared divided by 4 pi. And so we can substitute all this guy here. And we can put numbers, because now we know the value of the W boson, and we know the mass, and we know the value of the Fermi constant. And the surprise is that when we calculate this guy, it is 1 over 30. So it is much larger than the QAD Fermi constant alpha, right? Alpha is 1 over 137. So the question is, it is a weak interaction, it is stronger than QAD, who knows? The coupling is indeed stronger. So intrinsically, the weak interaction is stronger than the electromagnetic interaction. Okay, it is only the presence of the large mass term in the propagator that is responsible for the effective weakness of the weak interaction. But the coupling constant is stronger, is larger than the one of electromagnetic interaction. Okay, just to convince you about this, when we work in this low energy regime, so we can neglect Q square. The QAD propagator is 1 over 2 squared because the photon is massless. In this case, the propagator is 1 over m squared because we are neglecting Q squared. And so if you want to calculate the rate or the ratio of the rates for a charged current process and the QAD process, you have just to take the ratio of the square of the matrix element, which at the end corresponds to making the ratio of these two propagators. Okay? So it goes like Q to the 4 divided by mw to the 4th power. But since we are working in this approximation here in the low energy regime, this number is extremely small. Okay, so this tells you why, despite the charged current weak interaction is stronger than QED, at the end the probability for a charged current process is much smaller than a QED process. Okay, or is killed by the large mass of the W. What about the opposite regime? So when Q square is now much larger than W. So suppose we have a very high energy process, okay? So in this case, we can neglect the mass of the W. We are in the opposite regime now, okay? Extremely high energy. So the W mass term is now irrelevant, okay? And now the two propagators essentially became the same, 1 over Q square in both cases, okay? And this is indeed the manifestation of the electroweak unification that we will study at the end of the course, where electromagnetic and weak interaction merge into a single unified electroweak interaction. So with the same kind of coupling and the same kind of propagator indeed. Okay? So we are all tired. Any questions? All right. Okay, so see you next week. Have a nice weekend. Let me stop the screen.